Hello, students. This is week 3, day 2, and it is the beginning of new material. Okay, so we're leaving chemical reactions behind. We've practiced those enough and reviewed those, so now we're doing some new stuff. And a part of that new stuff is to talk about energy of a chemical reaction. Okay, so or a chemical change or even a physical change. When we talk about energy, we're in chemistry, we're talking about not kinetic energy necessarily, not potential energy. Some of these are terms you've probably heard before, but heat energy. Okay, heat energy is the energy that's important for our purposes for chemistry. And the variable for heat is a capital Q. Sometimes scientists will also use a variable that's as delta H for heat, where H, of course, is the heat energy. But oftentimes, and on this worksheet that we've given you, in this lesson that we've given you here, it's also symbolized as Q. Those are the same thing. All right. Now, for your purposes, heat energy is not something that you necessarily think about unless you're looking at how much heat energy you have consumed or used during a day to be able to function. Okay, and that heat energy is in the form of calories. Your body uses food and converts that into energy, and that energy then runs your body. And we think about that energy that you're getting from the food as in terms of calories. That is this heat energy understanding. Okay, that is this heat energy measurement. Now, in chemistry, we like to stick to metric units and SI based units, international units. So instead of the calorie, which is what you're used to hearing about and learning about and understanding when you talk about health and things like that, we use the joule. Okay, so the J here is named after a person named Joule, and it is our chemistry variable or chemistry unit for heat. But we're just talking about the same kind of thing, heat energy that is absorbed by something or heat energy given off by something. Now, this equation called the heat equation, as you can see from the term up here, this heat equation is for a physical change. Okay, so for example, if you want to make your coffee in the morning, all right, so you put the water in the pot, you put the cup underneath, you put the coffee grounds or the pod in your coffee maker, you hit go, and the first thing that happens is that coffee maker begins to heat up your water. Okay, now as it's heating up your water, it's producing energy from the electricity and converting that into heat energy, and your water is absorbing it. So what we're seeing or we're tasting later on is hot water, and we can actually determine how much energy was absorbed by the water with this heat equation. Okay, now there's 3 variables involved in this heat equation. One of those is M, and that is the mass. So it does matter how much water you have in the pot. The more water, the longer it has to heat up to get your water to the temperature that it wants to use for the pot. The less water you put in there, 8 ounces, would take less time and less energy because it's less than if you were making a 20-ounce cup of coffee. All right, so it does matter how much of the material you're heating up or cooling down. We also, to really kind of keep track of the energy change, is we use this delta T term. Okay, the triangle is called a delta in math, and it means change in. Okay, so a delta T, the triangle T, means change in temperature. And we generally measure that, of course, in Celsius. So your water would have started out at, say, 25 degrees Celsius right out of the tap, and you've heated it up to close to your boiling point. So maybe it's 90 degrees Celsius. So it's good and hot. Okay. Well, that's a change in temperature. So the initial temperature would be T1, and the final temperature would have been that 90 degrees. So the T2 is for final. That's what your substance ended up at. It started out at one temperature and it either heated up or cooled down. So if it cooled down, it would have ended up at a lower temperature. That would be the final temperature. If it heated up, it would end up at a higher temperature. Okay, the T1 is your beginning temperature. It's the initial. It's the starting temperature, and I'm spelling that wrong, so let me correct that real quick. But it's the initial temperature. It's the beginning temperature. Initial or starting temperature. The final temperature is where it ends up, ending temperature. And it always is the final, T2, minus T1. And what that does is it establishes a direction. Okay, so if it's cooling down, we can establish a direction because of the change that we're going to have is either going to be positive or negative. So in most cases that we're going to calculate, it will be heating up. So our final temperature will be bigger than our initial temperature, and we'll get a positive value. But the third term that's important here, not just the mass, not just how much the temperature changed, but also what the stuff is. Okay, so this specific heat thing is a specific term for that is substance dependent. It really depends on what you're working with. Think about metal. Okay, if you touch a piece of metal right now, it's going to feel cooler than if you touch a piece of wood or if you touch a piece of plastic. Okay, because metals and wood and plastic and water and every other substance that's around you that is absorbing the heat in your environment absorbs heat at a different rate. Okay, so we got the heat term, joules per gram. Okay, so that means that it's for every 1 gram, it heats up or cools down a degree Celsius. So that happens at a different rate. Metals heat up very quickly and cool down very quickly. That's why we use them as a conductor. Okay, that's why we use them as a pan to heat up our water or cook our food on the stove, is because we don't want the pan to have to absorb a lot of heat. We want it to pass the heat through to the substance that we're cooking. So we use a conductor which heats up and cools down very quickly. And we have a table of these specific heats depending on the substance down here. Okay, so we got water. Notice it's pretty high compared to these other things. But if you touched a piece of aluminum, you're going to see that it heats up or cools down very quickly because it takes very little energy for its temperature to rise per gram, or cools down in the case of as you're feeling it. But if you put it on the pan on a stove, it heats up fairly quickly or preheats fairly quickly before you put your stuff in there. Okay, so we've got different substances here with their different specific heats. All this matters in that this is a constant. Okay, so that as long as we know what substance it is that we're working with, we pick one of these for our C. So this is our C in the equation up here. And it does depend on what we're working with. All right, so we've got the heat term, which is usually what we're trying to calculate. We got the mass term, so it matters how much material we have, and that will be given. We've got the specific heat, which we pick from this table or has to be given, and we look for the final temperature and the initial temperature. Those three things together calculate the heat energy. All right, so as I scroll down here, we've got an example. Okay, so the example is how much heat energy does it take to raise the temperature of 100 grams? That's, of course, going to be our mass by 10 degrees Celsius. Now, by 10 degrees tells me that, let's say we started at 25, we'll heat it up to 35 to go up by 10 degrees. If we started out at 35, we'll go up to 45 to go up by 10 degrees. So this already is my delta T. So I don't have to do the final thing minus the initial thing because it already told me what the change is. This is the change already in the T, in the temperature. All right, so what about the C? We got to have C if we're going to calculate this heat energy. That's my Q. And we want to know how much heat energy, then where's my C? Well, the C, remember, is substance dependent. So if I look and I see, oh, it's water. So that's where I get my C. I come back up to the table up here and I see water is 4.184 with all these units. All right, so the specific heat of water from the table, which is my C, is 4.184 joules per gram degree Celsius. The mass is 100 grams, and the temperature increases by 10 degrees, so that is my delta T. All I have to do is substitute that into my equation. Q is equal to M times specific heat times this change in T. I know my change in T, okay, and it's 10 degrees, so that gets substituted there. I know my C, I looked that up on the table, so that's there. And I know my M because that was given. I then just multiply those three things together. The units are going to cancel and do what they do, but what you're going to end up with is 4,184. And since you're calculating this Q, you're going to put a little J there as the unit. So that's how this equation works. So let's do one of these together, okay? And then you can do the other ones by yourself. So we got how much heat, again, that's Q, does it take to raise the temperature? Okay, so we know the temperature is going up by 25 degrees Celsius. So that's the delta T. Now, what's it going to look like, you might ask, if it doesn't tell me by 25 degrees? Well, look down here at number 5, you've got two different temperatures. Okay, so with the two different temperatures, that's when you're going to have to do the T2 minus the T1. So you have to decide what it started out at, that's the T1, and what it ends up at, that's the T2. Okay, so I'm going to let you decide that on your own. But we also have this 100-gram thing. Okay, so that's our M. Now the question is, where's our C? So if we're solving for this in our equation, MC delta T, we know the M and the delta T. What about our C? Well, remember, that's the piece that's substance dependent. So we need to find the C of gold. So we come up there and we see, oh, the C of gold is 0.129. So I know what to plug into my equation now. This is the equation. I'm plugging these or substituting these values in for each of these terms. So the mass, so the Q is going to be equal to the mass, 100 grams, times the specific heat. Remember, I'm getting that from up there with the gold. It's 0.129 joules per gram degrees Celsius times the change in temperature, and it increased by 25 degrees Celsius, so 25 degrees C. I multiply through each of those terms, and I get my answer. Okay, so 100 times 0.129 is 12.9. 12.9 times 25, and I should have worked this out ahead of time, but I didn't. So let me figure that out real quick. So in your calculator, you would put 100 times 0.129 times 25, and you should get 323. I just rounded a little bit there. So 323 Q is equal to 323 joules. That's how you do each of these problems. All right, good luck.